Hello, good evening, and welcome to the 2021 January monthly lecture of the Varahamihira Science Forum. For those of you who are coming to this forum's monthly lecture for the first time, I will give a brief introduction of what we do, and then I'll hand over to Ramanan, who will introduce the speaker of the day, who will then give the monthly lecture of the month. All right, Varahamihira Science Forum was started in 2017 as a forum for science lectures, general science lectures at the general public. We've had a good run. We've had over 3 years of several lectures, nearly 40 lectures. And these are some of the lectures that you see. We have a website, varahamihirasf.blogspot.com, which gives all the announcements of the lectures and hosts the videos of the lectures after they are uploaded. And almost all of our lectures have been uploaded in the website, so you can go look up the website. We are also on Facebook, Twitter, and YouTube. This comes from a YouTube live feed. Facebook, our address is again just Varahamihira Science Forum. Twitter, it's Varahamihira SF. You can see these links also on the invitations for all our programs. And YouTube also, just search for Varahamihira Science Forum and you'll find it. Excuse me for that. And we are also have a couple of forums on WhatsApp, one just for event notifications, the other for group discussions. You can contact any of us on these numbers, Gopu, Mohan, or Ramki, and we will add you. We'll be happy to add you to either of those groups, and we can have discussions about various topics of science, including all the lectures that we have in this forum. We kind of started with this thought that Madras is considered the cultural capital of India. UNESCO declared it a musical city and so on. And a lot of interesting functions happen, including the Carnatic music season. It's a center of movies. We have cricket. We have other cultural festivals. We have temples and kolam and all kinds of stuff. But isn't science too part of our culture? But it doesn't get highlighted as much. There are scientific programs, popular lectures, but few and far between. There are professional seminars on several fields, engineering, medical, science, mathematics, but they tend to happen only at the institutes where those subjects are held with. For example, mathematics lectures may happen at the Chennai Mathematical Institute or Math Science or something like that. The technology, engineering lectures may happen at various colleges and the universities. Seminars on medicine may happen at medical college or a hospital. We wanted something that, and most of these are not really open for the public or even understandable by the public. So we wanted a forum where not only professionals but passionate amateurs can also speak and take science and technology to the general public, and that's why this forum. We wanted to build a community, use social media. So WhatsApp, Facebook, and YouTube tell us that story. We want the story, not just the facts, not just a dry narration, but we are kind of keen on style and substance. So that's why we have a mixture of amateur and professional speakers. It's entirely a non-profit attempt. We started off with a marginal payment for the participants in the early few lectures, but we got a few donations and we made some money, and then so we are done. Now this year, actually since March 2020, since April 2020, we are in lockdown mode, so we are doing it online. But any sponsors, hosts, volunteers, you're more than welcome. There is no membership fee to join Varahamihira Science Forum. All you need is an interest and something, an internet connection, something like that. So this is our YouTube channel. We have some of the it's got the videos of the previous lectures from the past. We also tried a couple of attempts at having lectures on Tamil. We will perhaps have a few in the future also. So there doesn't seem to be that much of a demand for that particular category. We want to also host certain lectures in schools and colleges. So we've had them on an individual basis. As a forum, we still haven't done it. And activities and heritage walks are in the future once the lockdown lifts. This is not, Varahamihira Science Forum is not the first forum to do such thing. We've had the Bertrand Russell Society in the past. We've had IIT host lectures by public figures like Arvind Gupta, astronaut Rakesh Sharma. We had the KSRI host Fields medalist Manjul Bhargava talking about Sanskrit and mathematics. We had a KV Sharma for Library and Foundation host the Bhaskaracharya workshop. We had a lecture on Lavoisier by Bharat Ratna CNR Rao. The Ekamra Nivas in Mylapore has hosted lectures by the Aladi family, including Kaladi Krishnasamy. Math Science has started this Science of the Sabha program every year. So they have been doing this for a few years. So we're not the only one. There are others doing it, but we are the only ones doing it on a monthly basis. And so we are pretty happy that it's been going on for nearly 4 years now. There are other events like this, activities. The Planetarium, Birla Planetarium in Kotturpuram opened its doors and put up exhibitions with the telescopes and casting it on boards and cardboard, providing glasses and all that for both the Venus transits and the Mercury transit. I like to say this over and over again. Madras is one of the few cities from which you can see a rocket launch. When ISRO launches a rocket from Sriharikota, this picture on the left is really taken from a rooftop. You can actually go to your rooftop and see the rocket launch. This one is or from any tall building. So if this one is from the Anna Centennial Library in Kotturpuram through a window, so you can go see that. Besides our regular activities, we also host certain courses. A couple of years back, we started a course on Indian mathematics and astronomy, and we've had 3-4 batches of this, including one a couple of these courses last year. We had the privilege of hosting one at the KV Sharma Library, and KV Sharma, for those of you who don't know, was a significant contributor to the study of Indian astronomy, who lived in Madras, and his collection of books is now turned into a library, and it's open for the public. And we hosted that, and then we also did an online version. Badri, one of our hosts, conducted a course on linear indeterminate equations, one aspect of Indian mathematics. Started off by Aryabhatta, mentioned in his Aryabhattiyam, and then continued by a couple of others later on, including 15th century mathematician who lived in Kanchipuram and wrote in Sanskrit. And Badri then continued and offered another course on Bhavana and Chakravala. These are second order indeterminate equations, that is quadratic indeterminate equations. This was originally found in the works of Brahmagupta in his Brahmasputa Siddhanta, but others like Jayadeva and Bhaskaracharya continue this, and much later European mathematicians like Euler and Fermat also explored that, and we had a course on it, and we probably offer these courses again for the general public later. Today's lecture is a combination of physics and computer science. We've had a variety of lectures in our forum. I won't go through all of them. These are some: Science Through Toys by Arvind Gupta, one of our best attended lectures. Weather and Climate in Sangam Poetry by a meteorologist, Dr. K.V. Balasubramaniam, talked about references to weather and various wind patterns and cyclones in Sangam literature. We had a lecture on Leelavati's Daughters, the women scientists of India, by Professor Uttara Durarajan of the D.G. Vaishnav College. And we had a lecture on wandering rivers and cruising coastlines by Singananjan, former geologist, president of the Geological Survey of India. On our physics lectures, we had a lecture on Principia Mathematica of Isaac Newton by Siddharth Chandrasekhar. We had one titled Atomic Theory for Almelupati by Akash Narayanan, who's researching in the Fermi Lab in Illinois right now. I did a lecture on Tamil about astronomy of ancient cultures and their mathematics. We had Dr. Satish Kumar Saravanan, then of the University of Leibniz, talk about a brief history of gravity. That was also a fairly well attended lecture. We had Akash Narayan again talk about the story of light, coming all the way up to quantum theory and C.V. Raman, starting with the Big Bang and so on. We had a lecture on C.V. Raman by Dr. K. Srinivasa Rao of Math Sciences. We had the children of Sevalaya School, Mahakavi Bharatiya School of the Sevalaya Trust near Tirunendravoor. Professor Swaminathan, retired professor of IIT Delhi, showed them how to operate a sundial, how to check the shadow and tell the time based on the sundial. He taught some teachers, and the teachers have been conducting certain workshops for the children, and the teachers gave a talk at our forum. We had Kathy Joseph, an avid YouTuber, talk about why science needs historical context. This just happened very recently, a couple of months back in November. And On computer science, we've had a trio of, we had a couple of IIT professors talk about it. We had Professor Ravindran talk about artificial intelligence. He gave an overview of what is this thing called artificial intelligence. We had Professor Kamakoti talk about chip design, fractal fabrication, etc. for the indigenous attempt, the story of the Shakti processor. And today we are proud to host Professor Prabha on quantum computing. With this, I will hand over to Ramanan to introduce the speaker of the day. Thank you.
Yeah. Thank you, Gopu. I'm happy to introduce Dr. Prabha Mandayam, the speaker for the day. Dr. Prabha Mandayam graduated with a master's in physics from IIT Madras. She obtained a PhD from Institute for Quantum Computing at Caltech. She worked as a postdoctoral fellow at the Institute for Mathematical Sciences and as an Inspire faculty fellow at the Chennai Mathematical Institute. She joined IIT, her alma mater, as faculty in 2014. Her research interests include quantum error correction and quantum cryptography. She has also co-authored a book titled The Functional Analysis of Quantum Information Theory. Her webpage has more details which we'll be sharing with you. And I just want to, Gopu mentioned Dr. Ravindran. I just want to thank Dr. Ravindran for giving the connection to Dr. Prabha. And once again, thanks to Dr. Prabha for accepting our invite and speaking here today. Over to you, Dr. Prabha.
Thank you, Mr. Ramanan, and thanks to Mr. Badri, Mr. Gopu, and the entire Varaha Mihira Science Forum. It's a pleasure to do this lecture as a part of this excellent series of programs which Mr. Gopu just now catalogued. So let me perhaps start by sharing screen and so indeed, the contact to the Science Forum itself came via Professor Ravindran, who is a faculty in the Computer Science Department at IIT Madras. And as Mr. Ramanan just mentioned, I am a faculty in the Physics Department in IIT Madras. And I have been working in this area of quantum information and computing for the past few years. It's been an interest for maybe more than a decade and more now. Let me just share my screen. So do you see my slides now?
Yes.
Okay. All right. So let me just dive into the lecture right away, since we're already starting perhaps a little bit late. Okay. All right. So could one of you just tell me if you can see my pointer on the screen? Can you see my pointer move? Okay, thank you. All right, okay. So I have titled this lecture as Quantum Computing Quo Vadis, of course, which means where is it headed, right? And I think this question kind of echoes a question in the minds of the public at large and anybody who takes interest in matters of science and technology today, because this has been a buzzword now, perhaps for almost 2 decades, if not more, though those of us who had an interest in quantum physics perhaps had heard of this in more sort of within the community. This word has been a buzz for quite some time, but perhaps among the public, maybe over the last decade, and a lot more so in the last few years, right? So the aim of this talk will be to introduce some of the terminology that is associated with quantum computing, the idea of a quantum bit. How is it different from a classical bit? So what is quantum computing? How does one compute with quantum bits? And of course, why should one be interested in it today, right? The hope is to also introduce perhaps some technical terms like superposition, entanglement, which are often bandied about, and maybe even demystify some of these terms, right? Okay, so I often like to begin with this quote of Serge Haroche, who won the Physics Nobel Prize in the year 2012. Perhaps Harosh's Nobel Prize can be considered as one of the first or the early Nobel Prizes to be given in the field of quantum computing itself, because he's been one of the pioneers of manipulating individual quantum systems down to a level that they can be called qubits, right? And he said in a recent interview, perhaps a few years ago, he had actually visited India. And in one of the interviews, he said that quantum computing is today trapped between hype and hope. And this, I thought, was a very fair statement of where the field is today.
I think we have a small electrical problem. We should be resolving it soon. Just stay with us, please.
Can we inform on the?
I have already done that.
Oh, yeah,
I've
thanks.
messaged in the YouTube channel as well
Okay.
as just now spoke.
Okay. So it's the second time it's happening today after we started.
Hey, can you hear me again?
Yes.
Yeah, I'm really sorry. We had a power outage here. I have now I'm using the Wi-Fi through my phone data, so maybe this will be more stable even against power cuts. All right, let me just get on with the presentation. I hope you can see my screen.
Yes.
All right, thank you. Thank you for your patience, and I hope we don't have any more interruptions. So let me just proceed to talk about some of the recent events which were covered prominently in the news. The main thing being this Google's claim of having, not just having a quantum computing device, but also having demonstrated what is called quantum supremacy, which is basically a terminology that has been coined to talk about the fact that quantum computers can have a certain power beyond conventional classical, what we call classical computers, conventional computers, which we tend to call classical computers, right? And this created a lot of buzz and generated a lot of interest in the field, both among academicians, among students, and also among venture capitalists and the like, and the likes, right? Of course, this was soon followed up with another claim from IBM, who also claimed to have uh, claimed that they were going to soon build a 53-qubit quantum computer. Today, they do have a 50-qubit device. And in fact, this device is now accessible in a kind of pay-per-use model, right? That one can actually go to a website, you can pay something to IBM, and you can run short programs on this quantum computer of IBM, right? So today we have a few more companies which have quantum devices, computing devices. There's a company called IonQ. There's a company called Xanadu, which use different kinds of architectures. And I'll just get into the architecture thing in a little while. But what do these quantum computing devices look like? So here are a few pictures. And we call these devices as noisy intermediate scale quantum devices. And hopefully by the end of this talk, it'll become clear why these are intermediate scale and why they are noisy. So this is what Google's 72-qubit machine looks like. This is the entire machine, which occupies a good fraction of a huge lab. But the quantum device itself is sitting in a little chip. And this chip is called the bristle cone, which has 72 qubits etched in here. And these are what are called Josephson junction-based qubits. They are superconducting qubits, where the underlying architecture relies essentially on etching Josephson junctions onto this chip. And of course, since these are superconducting devices, or the device operates on the principle of superconductivity, these devices, these chips need to be cooled down to almost liquid helium temperatures. And so they are kept in these huge dilution refrigerators. So while this little chip is at the heart of this device here, much of this device is about maintaining this chip at the right conditions, and in particular at the right temperature, right? And this is a startup based in Silicon Valley called Rigetti, which has this little 16-qubit chip out here, right? And this, again, the chip is sitting in the middle. This is the quantum chip. Of course, you may wonder at these numbers. What does it mean to say a device with 72 qubits? What does it mean to say that a device has 16 qubits? And again, this talk hopefully will clarify this. And this is what IBM's device looks like, not very different from Google's device, because both of them rely on the Josephson junction architecture on superconducting, the so-called superconducting qubits. And this is what IBM's Q1 processor looks like, which has 50 qubits, right? Okay, so with this sort of background and this sort of reason why one might want to be interested or be curious about this, let's now talk about what a qubit really is. What is a quantum bit, right? So we all know what classical bits are, or at least we have some heuristic understanding of what classical bits are. They are just objects that take one of two values, 0 or 1. If you're more mathematically inclined, or if you're a computer scientist, you will say that this is what is called a binary field, right? It's basically an object, which I simply call X, which takes one of two values, 0 or 1. So what is a quantum bit? Can I simply write a quantum bit as, well, correspondingly, there's another 0 here, and there's another 1. And I just put these symbols out here to denote that these are quantum bits, right? But that's not all, right? It's not that I simply have a quantum analog of this 0 and a quantum analog of this 1, this 0 and 1 are now quantum states, right? They are states of a quantum system. So this notation is something that I will periodically use during this talk, and this vertical line followed by this angle bracket. This is what we call a Ket vector in the quantum science parlance. I would say don't be too bothered by the notation. Just think of it as a way to distinguish your quantum bits from the classical bits. But like I said, it's not merely the notation that distinguishes them. They are different objects. They are different objects both physically and mathematically, right? And over the next few minutes, I hope to convey to you how different they are both physically and mathematically. So let's look at the mathematical aspect a little bit first. The point is my quantum bit does not only take two values, 0 and 1. A more formal way of saying it is that my quantum bit does not only exist in two states, 0 and 1, rather it can exist in what is called a superposition state, right? So this is what I call a superposition state, and A0 plus B1, right? I can have a state, my qubit can be in a state which is neither 0 nor 1, but is in some sort of intermediate state or in-between state, if you wish, right? Which is some linear combination of 0 and 1. To be precise mathematically, again, this A and B are not arbitrary numbers. They have to be complex numbers, whose modulus sums up to 1. And that kind of comes from the dictats of quantum mechanics and the properties of a quantum state. One can visualize this. It's often nice to visualize this distinction between the classical bit and the quantum bit via a geometric picture. And again, I'll come back to this geometric picture in a few slides. But in this slide, I just wanted to show this to point out that if I think of the surface of a sphere, all right, this is something we're all familiar with. A sphere is a geometric object that we're all familiar with. And I think of the north pole of the sphere as being the ket 0 and the south pole of the sphere as being ket 1, right? When I say ket, I mean the quantum state 0, the quantum state 1, or the qubit state 0 and the qubit state 1. My qubit can actually exist not just in this state 0, which is sitting at the north pole, and the state 1, which is sitting in the south pole, but actually my qubit can be in a state which is represented by any point on the surface of the sphere. So in particular, I can have qubits all along the equatorial plane like this. I've marked out some special states out here. We'll come back to these. But the point is my classical bit, of course, can exist only in two states, which is the north pole and the south pole. So when north pole represents my classical bit 0 and the south pole represents my classical bit 1, that's it, right? The bit can either take a value 0 or a 1. But my quantum bit can explore the entire surface of this sphere. It has an infinity of points on the surface of this sphere to explore, and that's what the power of superposition gives you. The fact that your quantum state can exist in a superposition of a pair of states like the ket 0, like the 0 and the 1, now gives me a lot more room to play with. And you can well imagine that this is where the so-called power of a quantum computer truly comes from, right? But this was a sort of mathematical description of how a quantum bit is different from a classical bit. Physically, can I sort of talk about this distinction from a physical point of view? So one classic example, and often intuitive enough for most people to understand, is the example of polarization states of light, right? We're all familiar with polarizers, right? We've all perhaps played with polarizing glasses of some form, right? So let's just quickly revise some high school physics here. So we know that light is a transverse electromagnetic wave. And we also know that light has both wave and particle-like properties. And these packets of energy that carry the energy of the EM wave are what are called photons, right? Now, if this black dotted line represents the direction in which my electromagnetic wave is propagating, or represents the direction in which the light is propagating, then we know that the EM wave can only be polarized in two ways because it's a transverse wave. It can exist in a polarization which is of this form, which is this up and down arrow, which is what we would call vertically polarized light, or the right extreme, which is what we would call horizontally polarized light. But of course, that's not all, right? The polarization could be in some intermediate angle, so long as it's a line or a vector that lies in a plane that is perpendicular to the direction of propagation, right? This is something that we all perhaps have seen in some form in high school, that the polarization of an electromagnetic wave has to lie in a plane that is perpendicular to the direction of propagation, right? So this is what I've written out here. The direction of oscillation of the electric field or the magnetic field specifies what we call polarization. And because light is a transverse electromagnetic wave, then you know this polarization has to exist in a plane that is perpendicular to the direction of propagation. Now, I can break down any intermediate polarization of this form, which is the middle figure out here, as having a vertical component and having a horizontal component. So now think of this vertical polarized light as representing the zero state of my qubit, the so-called ket zero that I wrote down in my previous slide. Think of this horizontally polarized light as representing the ket one, or the one state of my qubit. Then any intermediate state or any combination of horizontal and vertical is also a valid state of my qubit, right? So here, this polarization vector explores this entire plane, the entire plane which is perpendicular to the direction of propagation, right? So this is one physical realization of a qubit. This was, in fact, one of the earliest physical realizations of a qubit, the earliest experiments that were done to demonstrate certain interesting quantum properties or qubit-like properties were done using such polarization qubits, right? So let's play around a little bit more with this to understand this polarization qubit a little bit better. So now we know certain things already from polarizers, right? We know, for example, that if I have so what do my sort of Polaroid glasses do? They filter out certain components of the polarization vector, right? So if I have a polarization filter which is going to allow horizontal polarization, then such a filter or a polarizer will not allow vertically polarized light through. Similarly, I can think of a vertical polarization filter which will not allow horizontal light through. In a more technical way of saying this, now that I'm viewing my vertical and horizontal polarized states as quantum bits, is the vertical state and the horizontal state are mutually orthogonal, which means I cannot have vertically polarized light which has some horizontal component. I cannot have horizontally polarized light which has a vertical component. These two do not have any mutual components. However, I can have a 45-degree polarized light which has components both along the vertical and the horizontal, right? So I can have a 45-degree polarizer, which of course will allow a certain fraction of the vertically polarized light. It will allow a certain fraction of the horizontally polarized light, but it will not allow photons or light which are polarized at 135 degrees, because they again make an angle of 90 degrees between them, right? So I can pick out pairs of orthogonal polarizations. I can pick out horizontal, vertical. I can pick out 45, 180, 135, etc. So I can pick out pairs of polarization states which are orthogonal, and any such pair is in fact a qubit, right? And the state of a qubit is going to be any linear combination of such pairs of orthogonal states, right? So in the notation that we used, if we say that 0 is vertically polarized light and 1 is horizontally polarized light, then I can write down this 45-degree polarization as some combination of the 0 and 1, like I said. Of course, what will be the overlap? Well, 45, you know that cosine and sine of 45 is 1 over root 2. So you know that, so one can sort of write, it should kind of make intuitive sense that this 45-degree polarized light can be written as 1 over root 2, 0 plus 1 over root 2, 1, right? And this state is often called a plus state because you can also talk about the, I can talk about 45 and I can talk about 135. And 135, I simply have to one of these trigonometric functions will take a negative sign, right? So then I have I can make different superpositions. That's what I'm trying to point out here. I can make a horizontal plus vertical over root 2. I can make a horizontal minus vertical over root 2. And this would be a different state. And this pair of states, like we just discussed, will be another pair of orthogonal states, right? Okay, so now let me revisit this mathematical statement that I made. I can make it more formal for those of you who are familiar with a little bit of linear algebra or matrix algebra. One can say that a qubit is nothing but a complex linear superposition of a pair of orthogonal states, right? Which means that it is a two-dimensional complex linear vector space, right? Just to be more formal, physically, it corresponds to any two-level quantum system, and the polarization qubit is one such example that I have two orthogonal states. I have a horizontal and a vertical polarization, and this is what we would refer to as a two-level quantum system. So a general state of such a two-level quantum system is going to be some linear combination of these two orthogonal states, right? So one can write these states as matrices. I just want to conclude this somewhat technical part by showing you how we can map the states of the quantum bit to the surface of a sphere, right? Which is what I showed you a couple of slides ago. How do we get to the surface of a sphere? Well, we get to it because if you see this expression that I've written out here, psi is some general quantum state. Like I said, this is just some notation to tell you that it's a quantum state as opposed to a classical system, as opposed to representing a classical system. And this psi is some A times state 0 plus B times state 1. But this A and B can be complex numbers. They have to be complex numbers which sum to 1. Now, one can represent this in terms of two angles. One can represent this in terms of two angles, theta and phi, where theta represents the so-called amplitude part, right? Because the modulus of A now becomes cosine theta by 2. The modulus of B becomes sine theta by 2. And you know that sine squared plus cosine squared is 1. So that satisfies this constraint. This constraint, in fact, is what we call a normalization constraint, right? So I have mod A squared plus mod B squared is 1. And this angle, because I've written it as a half angle, can go anywhere between 0 and pi. But I have to also take into account the phase, because if you recall from the previous example that we did, I can have a 0 plus 1 state. I can have a 0 minus 1 state, right? Which means that there is something non-trivial happening in this, what we call a relative phase between the 0 and the 1, right? So this relative phase can be represented by a purely imaginary number e to the I phi, right? So this sort of by a phase e to the I phi, and this represents the phase part where phi is some angle between 0 and 2 pi, right? So this representation, what I've written out here as cos theta by 2 0 plus e to the I phi sine theta by 2 1 is a somewhat more convenient way of writing down the state of a qubit rather than just A0 plus B1, because it then allows me to visualize a qubit in terms of two angles, theta and phi. And again, if you can recall from, say, high school geometry, that you can, if I have these two angles, theta and phi, varying over two angles, theta and phi, where phi goes from 0 to 2 pi and theta goes from 0 to pi, this is something I can represent via the surface of a unit sphere. So this kind of a parametrization immediately brings to mind the surface of a unit sphere, because there's a certain spherical symmetry associated with writing it like this, right? So this then is what gives me a unit sphere here. So this is what I call a geometric picture of a qubit. Essentially, I can map the states of a quantum bit to the surface of a sphere, where, as I said before, you can think of the north pole as representing the 0, the south pole is representing the 1 state. The classical bit simply can access the north pole and the south pole, but now the quantum bit can be anywhere on the surface of the sphere, because theta is now the angle, the polar angle. You can think of theta as a polar angle and phi as an azimuthal angle. So the variation over the phi tells me the variation over this equatorial plane. And theta tells me the variation with respect to the angle with respect to, if you wish to call this the z-axis, then it tells me the angle with respect to the z-axis, right? And I can mark out, just like I've marked out the 0 and the 1, I can mark out other pairs of orthogonal states. The plus and the minus I wrote down earlier, they're simply combinations of the form 0 plus 1 and 0 minus 1. I can write down what's called a plus y and a minus y, etc. So this is simply to tell you that I can visualize my qubit as any point on the surface of this sphere, right? And these are just some states I've written down. This is for interested students to go ahead and work out. You can, for example, play around with this. You can write a little code, right? Where you can put this expression in Mathematica or MATLAB or Python or whichever is your favorite numerical tool, and try to see what thetas and phis correspond to what points. Of course, you can do this just by writing it down as well, and you can mark out these different states of a quantum bit, right? Okay, so this is what I wanted to tell you about how a quantum bit looks and feels different from a classical bit, with a little bit of mathematics and a little bit of a physical example, which was a case of the polarization qubit. So now that you have this quantum bit, what can you do with it, right? Now that I have established that it's possible to talk about superpositions of 0 and 1, what can I do with it? How do I compute with it, right? But before I do that, I just want to note down a few properties, how a few ways in which this quantum bit is different from a classical bit. One particular example is this idea of non-orthogonality and distinguishability, right? So we just spoke about how I can distinguish, or I can separate out the horizontal and the vertical polarizations. I can separate out the 45-degree and the 135-degree polarizations. But if I'm in a 45-degree polarized, if I have 45-degree polarized light, right, then sometimes perhaps some of you are familiar with the terminology of left circular and right circular polarized. So 45 degrees would just mean left circular polarized. 135 would be right circular, perhaps. If I have left or right circular polarized light, then my horizontal and vertical components do not get filtered out. There's a certain horizontal component that will come through and a certain vertical component that will come through, right? So this is what we call non-orthogonal, right? This is what we call non-orthogonality. So I can have my classical bits 0 and 1 are definitely orthogonal states, and they're always distinguishable. But because my quantum bit can now exist in a superposition of orthogonal states, my quantum states can be non-orthogonal. I can have my qubit in states which are non-orthogonal. The example would be that my 0 and my 0 plus 1 cannot be perfectly distinguished. This is another way of saying that I cannot separate out or distinguish the vertically polarized light from a 45-degree polarized light. I cannot devise a single polarizer which will tell me with certainty whether I have vertical or 45-degree polarized light, right? So this kind of leads us to the idea of a quantum measurement, right? When I measure a quantum bit, I have to project onto one of these two orthogonal states, right? So if I go back to this picture out here, of course, I have a lot of power in terms of exploring the entire surface of this Bloch sphere. But now let's say I'm in some arbitrary point on the surface of this sphere and I measure the qubit. I measure my quantum bit. When I measure my quantum bit, the measurement will collapse me down to either 0 or 1. Or I could measure in a different way and I can get collapsed to plus or minus. Or I could measure in a different way and get collapsed to plus y or minus y. But the point is that my measurement always extracts only a single bit worth of information, because it will tell me whether I have projected down to 0 or to 1. And that maps me back to a classical bit, right? So the quantum bit is allowed to explore this entire phase space. However, when I measure, I'm forced to project down to a pair of what we call orthogonal or distinguishable states, much like a classical bit, right? So this is the point that I wanted to make here, that I have states like the vertical and the 45-degree polarized light, which cannot be perfectly distinguished. So when I measure the 45-degree polarized light, which means that I want to find out, now whether this is, I want to find out, let's say I measure in terms of the vertical and horizontal axes, then I have to collapse down to either 0 or 1, right? So the information that I can extract from this is still a classical bit worth of information, right? Okay, so, and the way this collapse happens is in a probabilistic way. This is something perhaps we've all heard about. And this is where the non-deterministic nature of quantum states comes in, that when a state like plus is measured, and it's measured in what I call the 0-1 basis, which means that I want to project, I can only project it down to one of two orthogonal states, and I can project it down to 0 or 1. And when I perform a measurement which does that, then with probability 0, I get half. I'm sorry, with probability half, I get the state 0. And with probability half, I get the state 1, right? Because this is now in a equal superposition of 0 and 1, right? So this is another way of telling me that I cannot perfectly distinguish between the 0 and the 0 plus 1 by root 2, because the 0 plus 1 by root 2 is in an equal or uniform superposition of 0 and 1. So I'm equally likely to get a 0 or a 1. Right? So while I compute, I'm allowed to explore all possible states, but when I measure, I collapse down to one of a pair of orthogonal states with some probability, the probability depending, of course, on the final state. Okay, now I can write down what are called complementary properties of a system. The 0, 1, and the plus minus are what we would call complementary aspects of a system. Again, to go back to the polarization analogy, horizontal, vertical, left and right circular, or 45, 135 polarized, right? So I can either talk about or have information about the polarization in terms of vertical and horizontal, or I can have information in terms of it being 45 or 135, but I cannot simultaneously have information in both. And this statement may remind a lot of you of what is, of course, the well-known uncertainty principle, that quantum theory places a fundamental limit on the precision with which certain physical properties can be measured. The vertical horizontal versus 45, 135 polarization is one such pair of properties where you cannot simultaneously and precisely tell me information both in terms of horizontal vertical and in terms of the left-right circular polarization basis. Of course, the Heisenberg principle was originally stated. This is several of you may recognize this picture of Werner Heisenberg. And he formulated this principle for the well-known position and momentum observables. But here I'm stating this for a two-level quantum system. I'm stating this for, let's say, horizontal vertical polarization being one observable, and 45, 135 degree polarization being the other observable, right? And the same uncertainty principle holds in terms of these kind of, for these finite dimensional systems also, or these sort of two-level systems as well, right? So we already start seeing several differences between the nature of quantum information and the nature of classical information, right? This idea of having non-orthogonal states, of having states that cannot be perfectly distinguished, does not exist in the classical context, right? Whereas, of course, this is a prominent feature of quantum theory. Not just do you have states that cannot be perfectly distinguished, you also have properties which cannot be simultaneously measured, right? Okay, so armed with this knowledge, let's try to see how one can compute with quantum bits. I've just put down here a favorite quote of mine by David Deutsch, a physicist in Oxford, whose algorithm I'll just be talking about shortly. So he says that computers are physical objects and computations are physical processes. So what computers can or cannot compute is determined by the laws of physics alone and not by pure mathematics, right? And that's the essence of what we are seeing now, that if I decide to use quantum bits for computing, what can or can I not do, right? So firstly, how to compute, I must know how to manipulate quantum states. I must know how to perform logical operations on them, right? We have this sort of parlance of logic gates, right? We all know what logic gates are, and the simplest logic gate that one can think of for classical bits is the NOT gate, right? So classically, let's say you want to think of logical operations on a single bit, then the simplest thing you think of is a NOT gate, which transforms a 0 to a 1 and a 1 to a 0, right? So quantumly, what do I have to do? I have to have an operation which transforms my 0 to 1 and 1 to 0, right? But what is more, I'm now allowed superposition, right? I'm now allowed to have states of the form A0 plus B1. So what should happen to a state of the form A0 plus B1 under a quantum gate? Well, it should get mapped to A1 plus B0. And now we see that a quantum operation, a quantum gate operation, has to be something different from a classical operation. Classical operations are what are called Boolean functions, right? The NOT gate is a single bit Boolean function, which takes a single bit input and gives me a single bit output. Quantum gates are some kind of matrix transformations, right? Because I'm now transforming simultaneously a pair of vectors in a vector space, right? And I have to do this in a linear fashion. So these are now matrix transformations, and one can write this down as a 2 by 2 matrix, because remember, these are two-level systems. So if I want to represent this state, A0 plus B1, I would write it as a column vector AB. And the NOT gate, the quantum NOT gate, has to transform this to BA. And some of you may all be able to figure out, if you think a little bit, that this transformation, if you're familiar with a bit of matrix algebra, you can understand that this transformation can happen if I have a 2 by 2 matrix of this form, with node entries in the diagonal and 2 off-diagonal entries being 1, right? Physicists would call such a matrix as a Pauli matrix. This is one of the so-called Pauli matrices, and it's called a sigma X. This is for those of you who are maybe physics undergrads out here. This is nothing but one of the Pauli sigma matrices. This is a sigma X matrix. So we have, in trying to transform qubits, recovered objects that physicists know and understand very well. These are the Pauli matrices are examples of what are called unitary transformations or unitary matrices, right? So any 2 by 2 matrix, in the case of a quantum bit, any 2 by 2 matrix that preserves this normalization for me, which is that mod A squared plus mod B squared should be 1, any such matrix is a valid single qubit logical operation. And such matrices are what are called unitary matrices. I will not get into any further detail about their properties, etc. But suffice it to say that we understand these objects theoretically, and from a practical point of view, we now have ways in which we can implement these kind of logical operations. But of course, we know from classical computer science that it is not enough to have single bit logical operations. I want to be able to do what is called universal computation, which means I want to be able to implement any Boolean function, and I want to be able to implement, let's say, any n-bit Boolean function. Classically, we know that this is possible if you have some sort of elementary set of gates. If you have an elementary gate set, you can build circuits and computations out of these elementary gate set, right? So what is the quantum analog of that? Do we have this idea of universal quantum computation? Well, of course we do, but for that we need to go to multi-qubit gates. Single qubit gates will not suffice, right? So classically, you know that universality can be achieved provided you have and or not, right? That is one universal set with the XOR, or you need to have the NAND gate by itself can be a universal gate. The NOR gate by itself can lead to universal classical computation and so on, right? But the but the main point out here is that you need a 2-bit gate. You need a gate that can take 2 bits as input and gives me 2 bits as output, right? Similarly, to have universal quantum computation, I need a 2-qubit gate, right? And this 2-qubit gate that is often used in most of these architectures is what is called a controlled NOT gate. It's a controlled version of the NOT gate where I essentially implement the NOT gate on one of the 2 qubits, which I call the target qubit, provided the first qubit, which is called the control qubit, is set to 1, right? So this is a controlled NOT operation on the second qubit, on one of the 2 qubits, which is called a target qubit. So here's an elementary quantum circuit which describes the controlled NOT gate. I have out here a quantum bit X, a quantum bit Y. They're both inputs to the circuit. This symbol out here represents the 2-qubit gate for me. And this is a gate that somehow couples these 2 qubits, because what happens to the second qubit depends on the state of the first qubit. And the second qubit gets flipped if the first qubit is 1. One can write this out in terms of a Boolean function, namely the XOR function, right? This symbol out here represents for me the classical XOR Boolean operation, Y XOR X, which flips the value of Y provided X is 1, right? So this can be thought of as a quantum XOR gate. Of course, one can write down a matrix representation for this as well, but that was just for those of you who want to sort of go back and work out a matrix based on this. But the point is that once I have a 2-qubit gate like this, then any multi-qubit logic gate can be implemented using such a controlled NOT gate and single qubit gates. And single qubit gates, as I showed you, are simply unitary matrices, 2x2 unitary matrices. And in fact, one has a basic set of such gates, right? The Pauli matrices being prominent among the kind of gate operations that we would like to perform. So having shown you an elementary gates and an elementary circuit, let's now talk about what you can do using superposition, right? So now I'm truly entering the computational or the algorithmic part of this talk, where I would like to talk about what I can do using the fact that quantum bits can exist in a superposition of 2 states. So this idea is often called quantum parallelism, the idea that you can evaluate a function, for example, for many different values of the input simultaneously using a quantum computer. But this statement has to be made with a pinch of salt, as we will see. So it is true, like I said, that using a quantum bit, because the quantum bit can exist as a superposition, right? One can sort of see that because of that, it may be possible to have this feature of parallelism. However, we come back to the fact that when you measure, you will again have to collapse down to one of a set of orthogonal states. So it's a rather challenging task, in fact, to devise quantum algorithms which take advantage of quantum parallelism, while at the same time circumvent this problem that the measurement is going to collapse you down to one of a set of orthogonal states. And essentially, you're only going to be able to retrieve as much information as you can with a classical bit, finally, right? Okay, so here's an example. So if I think of any single bit Boolean function, which takes a single bit 0, 1 to another single bit 0, 1, now I can devise a quantum circuit, okay? So this is a quantum circuit. You might even think of this as some kind of a black box, right? Where you know that a classical device can only evaluate such a function in a sequential way. So if I have a calculator or a computer with me, I can first evaluate f of 0. I can find out what that is. I can evaluate f of 1, and I can find out what that is. But quantumly, it is possible for me to simultaneously evaluate f of 0 and f of 1. Evaluate. But it's not clear if I can actually extract out the value of f of 0 and f of 1 simultaneously, right? So how do I evaluate f of 0 and f of 1 simultaneously? I can design a 2-qubit quantum gate or a quantum circuit, a 2-qubit quantum circuit, where the first qubit is now in a superposition state. And remember the state which I had shown earlier, the 0 plus 1 state, right? So if I were to call this abstractly as x and y, I can imagine that there is a kind of a quantum gate which computes for me x, which leaves the first qubit in x, and computes for me y XOR f of x in the second qubit, right? So in this fashion, I can actually simultaneously compute f of 0 and f of 1. Because now, if my first qubit is now in a superposition of 0 and 1, what does the gate do? When this qubit is 0, it does y XOR f of 0. When this qubit is 1, it does y XOR f of 1. And if y is 0, then it essentially gives me f of 0 when x is 0 and f of 1 when x is 1. But now I'm doing this in a superposed way. So I have at my output a superposed state which somehow has information about both f of 0 and f of 1, right? Okay, so a single quantum gate can evaluate both f of 0 and f of 1 in a superposed state. However, what value you want at the end of it has to be obtained only by a projective measurement. So now if I perform a projective measurement or by a measurement on the first qubit, if I collapse my first qubit, it can collapse down to 0 or 1. And when the first qubit collapses to 0 or 1, what I have in the second qubit is an f of 0 or an f of 1, depending on whether the first qubit collapsed into 0 or 1. And that, as we saw, is a probabilistic process. So I will, at the end of the day, only evaluate f of 0 or f of 1 in each trial of this, right? But I have the ability to design gates which can simultaneously compute f of 0 and f of 1. So can I use this power of being able to compute f of 0 and f of 1 in some way? And this was a simple algorithm designed by David Deutsch. This is a kind of toy problem called the Deutsch problem, often called the Deutsch algorithm today. And I want to quickly take you through the main points of this, just to give you a feel for what a quantum algorithm does and how does it derive its power, right? So here's the problem that has to be solved, right? So let's say that we have that it's a two-person game, right? That there are two people out here, Anita and Bharat. And the game that they play is the following. Anita, whom I shall simply call A, selects some number between 0 and 2 to the n minus 1. This is another way of saying that Anita is picking some n-bit string, right? Remember, there are 2 to the n-bit strings, right? So this will correspond to picking some number between 0 and 2 to the n minus 1. She picks a number and she sends it to Bharat, right? Bharat has to evaluate some Boolean function of this n-bit string. It's a Boolean function which has a single bit outcome, right? And send the outcome 0 or 1, whichever it is, to Anita, right? So Anita's goal is to determine whether this function, which Bharat has picked, is constant or balanced. So this is the game, right? Bharat says, I'm going to evaluate some function, and this function could be a constant function or a balanced function. That's a promise that Bharat makes to Anita. He's not going to pick an arbitrary Boolean function, but a function which is either constant or balanced. A constant function simply means that f of x takes the same value for all values of x. A balanced function means f of x is 0 for half the values and f of x is 1 for the other half, right? So how many trials or how many times does Anita have to query Bharat in order to know whether the function is constant or balanced? So how quickly can Anita succeed? So this kind of a model where you have one party querying another party. So this is called a query, right? Each number or each n-bit string that Anita sends to Bharat can be thought of as a query that she asks Bharat. And Bharat's job is to compute this function and send the outcome, right? Anita doesn't know what the function is, but by repeatedly querying Bharat, she has to find out whether this function is constant or balanced. This is a kind of computational model which is often called an oracle model of computing. Bharat is like an oracle to whom Anita is asking questions. And the oracle simply gives a binary answer, 0 or 1, right? And by repeatedly asking questions to this oracle, Anita is somehow supposed to determine what is the function that the oracle, not what is the function, but whether the function is constant or balanced. So how quickly can Anita succeed? Like I said, this denotes something called query complexity in this oracle model of computation. How many times does Anita need to query Bharat, right? So classically, Anita has to query Bharat at least 2 to the n by 2 plus 1 times. This is again something that you can think about and work out. So for example, if I just had a single bit function, right? So if I just had a single bit function, how many times does Anita need to query Bharat? If it's a single bit function, Anita has to find out whether f of 0 is equal to f of 1 or not. But for that, she has to send 0. Bharat has to compute f of 0 and tell her. She has to send 1, and Bharat has to compute f of 1. And then she can compare f of 0 and f of 1, and she can conclude whether the function is constant, right, which is what it would be if f of 0 is equal to f of 1, or if it's balanced, which is what it would be if f of 0 is not equal to f of 1. So she needs 2 queries. She needs to query 0, she needs to query 1. Now you can start scaling it up. If it's a 2-bit Boolean function, she has to query at least half the number of strings there are. So she has to send 0, 0, 0, 1. But that alone will not suffice. She also has to send 1, 0. And depending on whether that is the same or different as 0, 0 or 0, 1, she can conclude whether it's a constant or balanced function. And now you can keep building this argument up in an inductive way. And you can see that Anita will have to ask at least 2 to the n by 2 plus 1, right? And this is basically the total number of bit strings by 2 plus 1. But quantumly, the amazing thing is that she can do this using simply one query. So she can question the oracle just once. If she had at her disposal quantum states, right, she can question the oracle just once. And based on the answer to this one question, she can conclude whether this function is constant or balanced, even though it's an n-bit Boolean function. And classically, you need something which is exponential in n. You need something which is 2 to the n minus 1 plus 1, right? So something exponential in n, but quantumly, she can do this with a single query, right? And this, again, is basically, she's drawing upon the fact that quantum states can exist in superposition, right? But the challenge lies in devising the query in a clever way, right? Okay, so she queries with a single superposed state. Now, because she's querying in a superposition state, Bharat is going to evaluate multiple values in a parallel fashion. We saw how we can do this using a simple 2-qubit example, right? But now the outcomes or the output is stored in a superposed state. Anita now has to do some clever manipulation of the final superposed states to decide whether the function is constant or balanced. I have written out this circuit here, and I think it's a bit too much detail to get into the details of this circuit. But let me just say that rather than simply measure the earlier figure I had, I simply said you can measure the first register, the first qubit register in 0 or 1, right? So rather than simply measure the first register, Anita is now going to perform some gate operation here and do something more in order to extract this information. Remember, Anita's goal is not to evaluate f of 0 and f of 1. Rather, her goal is to compare f of 0 and f of 1. And it turns out that you can do this, that if f of 0 is equal to f of 1, you will get one output state. And if f of 0 is not equal to f of 1, you'll get a different output state. Again, let me not go over this notation and the details, but suffice it to say that she can devise a clever method at the output to extract this information of whether the function is constant or balanced. And she can do this. This is just a 2-qubit example, right? Where it's actually a single bit example, right? Even with a single bit, you can see the speed up, right? Classically, I need 2 queries. Quantumly, I can do it with a single query. But with an n-bit scenario as well, I can simply do this with a single query where I have to make all these n-qubit states into a superposition state and query the oracle or Bharat just once. Okay, so this is some more details of this. I leave it in my slides for those of you who are familiar or who would like to play around with this notation. You can sort of actually evaluate this very easily. It's one of the simplest quantum algorithms to work out and evaluate with a little bit of knowledge of algebra, linear algebra, right? So by measuring the first register in a clever way, Anita gets to know whether the function is constant or balanced. A single qubit quantum algorithm is twice as fast as the classical one because the classical one needed 2 queries, but the quantum one just needs 1. An n-qubit algorithm is exponentially faster because the classical algorithm needed something of the order of 2 power n, right? 2 power n minus 1. But quantumly, need again a single query, right? So this toy problem of this Deutsch problem and the quantum algorithm which resolves this in a single query is just to give you a kind of sneak preview into the power of quantum computing, right? Of course, there are many more quantum algorithms which have been worked out for various practical problems, problems that one might actually like to solve and not these sort of toy problems, but in a realistic scenario, one may need to solve some practical problems. Well, there are practical problems that can be solved efficiently. One of the most important quantum algorithms is the quantum search algorithm, right? So if I want to search through an unsorted database of size n, classically this requires of the order of n operations, but the quantum Grover search algorithm requires only square root n operations. Similarly, factoring an n-bit number requires something of the order of n log n operations, but the quantum algorithm, due to Peter Shor, requires only log n squared operations. And again, you can see that the speed up in this case is what we would call quadratic, because you've gone from n to square root n operations. The speed up in this case is what we would call exponential, because we've gone from order n log n to something which is purely a polynomial log n squared, right? So this is an exponential speed up. And in some ways, what lies at the heart of the factoring algorithm is in fact what we call a quantum Fourier transform, which relies on the kind of superposition that one described in the case of the toy problem, the Deutsch problem, right? So this kind of concludes the quantum computing aspect of what I wanted to talk about. So just to give you a more zoomed out picture now, we have computer scientists often like to talk about this complexity landscape, right? You have these complexity classes which define or which kind of formalize this notion of how hard a given problem is, right? So many of you may be familiar with this class of problems that is supposed to be P, which means that they require either polynomial resource, which requires some kind of polynomial resources to solve it. So one way of saying it is that there's a class of problems P which requires polynomial size circuits to solve the problem, right? Then there is a class of NP problems which cannot be solved using a polynomial size circuit, but rather can be verified using a polynomial size circuit. And this factoring problem, which is basically the problem of factoring a number into its prime factors, right? That's what the factoring problem is. And that's what, it's this problem of factoring an n-digit number, I should have written out here, into its prime factors, right? Factoring means what? Into its prime factors. So this is an important problem from various computing perspectives, but mainly from today from a cryptographic point of view. And this problem classically is known to be in the class NP, right? At least, well, right now we don't have a polynomial time or a polynomial space classical algorithm which does factoring. But of course, if you're given some set of prime factors, you can verify within polynomial time if these are indeed the prime factors of this given number, right? So it is in the class NP. The quantum complexity landscape is somewhat messy at this point. We don't completely understand this, but it is something like this, right? Where you have this class of what are called bounded polynomial quantum algorithms, which are basically quantum algorithms which can solve a given problem in polynomial time or in polynomial using a polynomial size circuit, right? But in a random way, right? A quantum algorithm really cannot be compared to a deterministic classical algorithm completely in that sense, because there is a certain inherent randomness. We saw this even in the Deutsch problem, where you had to devise some clever operations at the output to extract the information out, right? So this is what the quantum complexity landscape looks like. We know that any classical problem which can be solved in polynomial time can be solved by a quantum computer also in polynomial time. There are certain problems for which no classical algorithm exists which can solve in polynomial time, but there exist quantum algorithms which can solve in polynomial time, factoring being the prime example of that. But then there are also all these classes of classical problems which are NP, which are hard, but for which we do not have quantum algorithms yet. So the big question today in quantum computing or quantum computer science, if you will, is whether the class NP, the classical class NP, actually lies within the quantum class BQP, right? So this is a kind of, just to tell you what the quantum computing landscape looks like today. So this is what I call bounded error quantum polynomial time. So before I proceed, maybe I just like to know how much time I have, and then I can tailor.
How much time do you need to complete this?
Can I take 15 more minutes?
Yeah. Go ahead. No problem.
Okay, fine.
And then
there
we
were
will
some
have a
messages
question
in
and
chat.
answer
Are there
session.
questions that I should answer
Yeah.
at this point, or?
No, we will have all the questions at the end once you complete your talk. Then
Okay.
we will have a conversation.
All right. Okay. Sounds good. Okay. So let me then proceed to talk a little bit about certain other aspects of quantum information. I have just focused on the computing aspect, right? I have spoken about quantum gates, quantum circuits, and quantum algorithms briefly. But let me talk a little bit more about certain other interesting and sometimes somewhat cool aspects, what are considered cooler aspects of quantum information. So, of course, information is physical. This was also the essence of the quote that I had shown you earlier from David Deutsch. This quote is from Rolf Landauer, who was a pioneering computer scientist at IBM, who also dwelt on the implications of using quantum states to store information, right? So one of the first things you learn about quantum information is that it's not all rosy. It's not that because you have superposition, now you have superpowers. Well, no. There are certain classical operations which are considered sort of basic classical operations that you can do, which you cannot do in the quantum case. And the simplest example of this is copying. Classically, copying is, of course, the easiest task. As students, we all know this. I mean, in general, we know this, that copying is a rather easy task. I have copied, for example, for this talk, several figures from various sources. I have taken down several quotes from various people, etc. So copying classical information is one of the simplest things you can do with classical information, but you cannot copy quantum information. A more formal way of saying this is via what's called the quantum no cloning theorem. This was, in fact, this goes back to a Nature paper way back in 1982, right? So even as far back as 40 years ago, there were physicists who were worried about, or who were studying the implication of storing information or using quantum states as a sort of information processing tools, right? So the first thing that they noted is that an arbitrary quantum state or an unknown quantum state cannot be copied, right? There is no universal quantum copying machine. There is no quantum Xerox machine which is going to copy quantum information in an arbitrary fashion. So this again goes back to the details of how quantum states can be manipulated, the fact that they have to be some special kind of transformations, they have to be linear, they have to be in particular unitary, and so on. So what was shown is that if indeed, so if I think of this box, which I have represented with a U and 2 question marks, if I think of this box as a kind of quantum copying machine, then if such a machine were to make perfect copies of 2 states, then either they must be the same state or they must be orthogonal states. But as we saw right at the beginning, orthogonal states are simply classical states in some sense, right? They're just like 0 and 1, which are simply the north and south pole of this quantum Bloch sphere, right? So either I can have states which are exactly like classical states which can be copied, or I can devise a specific copying machine which can copy a specific state. But I cannot devise a quantum Xerox machine which will going to copy any state that I give it, right? This circuit is just a way of saying that I have the state that I want to copy here, and this is like a blank register out here. And this blank register, which is my empty page, has to have a copy of the state sign. This is what an ideal copier should do. But one cannot, the laws of quantum mechanics forbid such an ideal copying machine, right? So this is one of the prominent don'ts of quantum information. It's one of the prominent no-go theorems of quantum information, and there are a few, but this is the one which has far-reaching and deep implications. The fact that you cannot copy quantum information. Okay, so But then on the other hand, you can do something very cool, which is that you can teleport quantum states, right? So while I cannot copy a quantum state in this fashion, that I put in the state in one register, I put in a blank state in one register, and I end up with 2 copies of the state. I cannot do this. But what I can do is quantum teleportation. And let me just quickly tell you a little bit about teleportation, since this word also gets used a lot. And this is the fact that you can teleport is related to the fact that you have what is called entanglement, right? That quantum states can not just exist in superposition, but can also be entangled, right? So, what's entanglement? Again, little bit formally, I just wanted to introduce the idea of entanglement. Now, entanglement basically is a term that is used to describe correlations between quantum states beyond what classical physics allows, right? So automatically, I need to now think about 2 quantum systems. So let me think in terms of 2 qubits, right? So let's say I have these 2 qubits, right, which could be 2 what I call spin half particles. They could be 2 photons, for example, right? And I can write down now states of this 2 qubit system, right? So 2 qubits can be in, what are the possible states? Well, they can be 0, 0. It's like a 2-bit string in some sense, the quantum analog of that. So I can have 0, 0, I can have 0, 1, I can have 1, 0, and I can have 1, 1. You can just ignore this cross symbol here for now. It's just, for those of you who are slightly more technically inclined, this is a cross product or a tensor product, okay? I've just put the symbol out here, but you can just ignore it. It's just 0, 0, 0, 1. They're just labels now, right? But now I can make superpositions of these, right? Because now these are 2 quantum bits, not 2 classical bits. So then I can make states of the form 0, 0 plus 1, 1, 0, 0 minus 1, 1. I can make 0, 1 minus 1, 0, and so on. And here is a quantum circuit that will achieve that. Again, this is for a little bit extra for those of you who would like to go work this out. But let me just note that the kind of states I've written down are precisely what is known in the literature, both popular and technical, as EPR pairs. EPR, of course, stands for Einstein, Podolsky, Rosen, who came up with this idea of entangled states in a seminal paper in 1932, and who also, I mean, not just came up with the idea of such states, but they came up with the physical implications of being able to prepare such states. The fact that you're allowed to make such entangled states means that you're allowed to have certain kinds of correlations which are forbidden in classical systems. These are also known as Bell states, after the famous particle physicist John S. Bell, who formalized the notion that of EPR, right? Who kind of gave a mathematical expression to what EPR had written out in their 1932 paper. Okay, so entangled states, to put it simply, are not product states, which means that they do not admit a local product decomposition. I'm writing down a 2 qubit state, but if you look at the superposition, the 0, 0 plus 1, 1, I cannot break it down into a state of the first qubit times a state of the second qubit. I cannot factor it locally. I cannot write it as a local product state. A more formal way of saying it is I cannot write it like this. I cannot write it as some psi and some phi, right? So in some sense, I have more information about the whole than about the parts in an entangled state, right? This can even be formalized using the notion of entropy, the fact that I have more information in the whole than in the individual parts if my 2 quantum states are in an entangled state. So now what can I do with an entangled state? Well, I can teleport. So here's a kind of cartoon picture of what the teleportation protocol does, right? This is from a paper that goes back to 93, but the original teleportation protocol is, of course, due to several people, starting with Charlie Bennett, William Wouters, several of the pioneering physicists and computer scientists from the early days of quantum computing and quantum information processing. So the protocol goes as follows. Again, I have 2 parties, Anita and Bharat. I have, excuse me, I have a photon here. This green wavy line here represents a photon. Anita has a lab out here, and Bharat has a lab, which are physically separated in some way, right? A more physical way of saying this would be that they are sort of, uh, they are not within each other's light cone, so one cannot signal between A and B. Suffice it to say that they're just physically separated in two separate physical locations. What teleportation achieves is there could be an incoming photon which is in some state psi, right? Which is sort of prepared in Anita's lab, or which somebody gives to Anita, right? Some source gives to Anita. Now, by using certain elementary quantum gates, Anita and Bharat can achieve the following. The state can be destroyed in Anita's lab and reproduced exactly in Bharat's lab, right? And this is exactly the idea of quantum teleportation. Of course, note that this is not copying, because the state truly gets destroyed in Anita's lab and reappears, or can be sort of realized in Bharat's lab, right? So it's not as if at the end of the day, one ends up with two copies of the same state, but rather one has found a way of physically transporting, if you will, the state from this lab to the other. But the key resource that this needs is what's in red out here, which is an EPR pair, which is an entangled state. So Anita and Bharat need to share an entangled state. And if they share an entangled state, they can, using a series of elementary operations, take some unknown state. So Anita does not know what the state is, the state psi, right? And in fact, if Anita tries to find out what the state is, she will end up destroying it, because she has to measure. Measurement will collapse. It will break the superposition. So she will end up destroying the state in some way. But if she does certain clever operations in conjunction with Bharat, then she can, together, they can realize the state in Bharat's lab. But of course, the state will then no longer exist in Anita's lab, right? So this is a kind of space-time picture of a teleportation protocol. Again, one can represent this using a quantum circuit, which I will skip for now, but just to, I just want to mention here that as recently as December of last year, December 2020, NASA has sort of realized quantum teleportation over a non-trivial distance of about 100 kilometers over a fiber optics channel, right? So quantum teleportation experiments are very much on even today. And of course, this is now only over a 100-kilometer channel, right? But the point is, it's very much a reality today, and it's very much a feasible quantum protocol, provided you have a way of sharing entanglement between these two distant physical labs, right? Okay, so let me proceed. This is a circuit that implements teleportation, but I'm not going to dwell on all this. So let me just cut to the end of my talk. I did put in some slides about what makes quantum computing hard to realize in practice, right? So let me kind of conclude with that in a couple of minutes. So this is David DiVincenzo, again, one of the pioneers of the idea of quantum computing and quantum information processing. So now we have talked about the theory of it. We have talked about what is possible, what is not possible. But what about the practice of it? Well, this is the kind of desiderata that one needs in order to be able to implement a quantum computer. And let me skip down further to several slides down. So I just want to mention this word decoherence here, right? So today, the biggest bottleneck in implementing quantum computing or any kind of quantum information processing task like teleportation is decoherence, right? The fact that quantum states quickly lose information because of interactions with the environment. And let me just cut down. Okay, so let me just show you this, a couple of more slides maybe. So people often talk about a quantum Moore's law, right? I suppose several of us have heard of the Moore's law, which talks about how our chips are getting smaller and smaller. This is a Roger Moore's law for the semiconductor industry, which talks about how you're going to be able to implement more and more transistors and other components in smaller and smaller areas. There's a kind of inverse Moore's law for the quantum case, which talks about how many qubits can you realize? So this is the number of qubits on the y-axis, and this is time, literally, from 1990 to 2020. And this shows different experiments that have been done on different architectures, right? Starting with, this must be NMR quantum computing in 1995, all the way down to Google and IBM's quantum computers in 2018. Today, we may have something close to 100 actually already here, right? So you can sort of fit this again to a linear scale like this. And the idea is that roughly every 7 years now, we are doubling the number of qubits that it's possible to implement and the number of qubits that it's possible for us to manipulate in a coherent way without losing the information, right? So today, this is the key challenge in building any quantum computer. This again tells you something about the lifetimes of qubits as a function of the year. And the takeaway from this is that the qubit lifetimes are also increasing in some linear fashion. And again, these are various physical architectures that implement qubits. So let me just conclude with this quotation here from John Preskill in a very recent article called Quantum Computing in the NISQ Era and Beyond. So Preskill, again, one of the early pioneers of the field, he coined this term, noisy intermediate scale quantum technology. And if you recall, this is what I started with. So why is this noisy intermediate scale quantum technology today? Well, because we have quantum computers with 50 to 100 qubits, which are able to perform certain tasks, surpassing the capabilities of today's classical digital computers. This is what Google's bristlecone chip achieved. However, the limiting factor today is the noise, both in realizing the quantum gates as well as in implementing the quantum bits itself, right? And what we need is quantum error correction to be able to implement what is called quantum error correction in order to be able to surpass this barrier that decoherence or noise imposes on us. Okay, so let me stop here, and I hope I gave you some idea of what it means to talk about quantum bits, quantum gates, quantum computing. And I have a slide with some references which I can share in the end, right?
Yeah.
Thank you.
We want to share the reference now.
Okay, sure.
You can just have the screen on that page while we talk.
Let me do that.
And if you need to change the slide to show anything while our conversation happens, you could do that as well.
All right. So let me show you the references. The first two are somewhat recent books on popular level books on quantum computing. So this is John Gribbin, who has written several interesting books on quantum physics itself, right? His books on quantum physics are also highly recommended. Also, this more recent book, Computing with Quantum Cats, from Alan Turing to Teleportation, which was something I briefly touched upon. Scott Aronson, well-known quantum computer scientist from University of Texas. His book on quantum is called Quantum Computing Since Democritus, who's of course the Greek philosopher, as we know. And this again is a book which is about a few years old now. Some of you may have already read or heard of Simon Singh's The Code Book. This is a book that I would recommend to understand why prime factorization is an important computing task today, and why Peter Shor's quantum algorithm for factoring took the world by storm, literally, and why it generated such a huge amount of interest in quantum computing. So this is a book that talks about cryptography, and the byline of the book, in fact, says from whatever the Greek or the Roman ciphers all the way down to quantum cryptography, right? This is an article by John Preskill, from which I quoted. The last three are somewhat popular level articles written by some of the important quantum computing scientists today: John Preskill, Carlton Caves, and Ivan Deutsch. The references are, for certain journal articles, but these are articles which should be accessible to people with sort of basic knowledge of high school physics and mathematics, right? And hopefully this talk makes some of these articles more accessible to you. Yeah.
Thank you. Thank you, Professor Prabha. Can you just keep that the reference page itself for now?
All right. Okay.
And then we can always go back to any other page.
Sure.
And thanks for all the references. I've read a couple of books of John Gribbin, his a general introduction to a popular introduction to the quantum mechanics, but also his biography of Erwin Schrödinger.
Correct.
Which I enjoyed quite a bit. So I will certainly pick this book. I have not read this one. I will get hold of it and read. I have some. There are a few questions from the YouTube channel, but I have some fundamental questions. Now, in the classical computing, we started building those computers with vacuum tubes, and then we moved to silicon. And thereafter, we have progressed very fast in terms of the number of the diodes and triodes and various other things that we can squeeze into one integrated chip, basically. Now, what are these quantum computing chips made of? Is it silicon? Is it something else? Is it a special form of it? Can you give me some idea about that?
Yeah. So, okay. So the superconducting qubits are basically, they are some kind of, it's a kind of silicon germanium 2D material, right? So basically they're etching on some kind of 2D material, and they're etching these nano-sized Josephson junctions onto this kind of 2D materials, right? So that's essentially what the superconducting qubits are made of.
So effectively, the CPU is, again, I'm just trying to compare with whatever little that I know of the regular computing to the quantum computing. So your computational brain is basically the material that you talk about, right?
Right. So today, Intel, I think, is also invested in building purely silicon-based, what are called solid-state qubits, right? Using single quantum dots in silicon, right? So, but that is a technology which hasn't progressed, say, as much as the superconducting qubits have, right? The advantage with the superconducting Josephson junction, so let me just explain to you what the qubit is. I didn't have a chance to do that. It is basically the presence or absence of a flux in the Josephson junction, right? That's what my 0 and 1 are. And these two states are energetically well separated, which is what I need to have a relatively stable qubit, right? So the superconducting qubit is one of the more stable qubits that we know, right? But it's by no means clear that this is going to be the winning architecture because the superconducting qubits have to be maintained at very low temperatures. You have to build these huge dilution refrigerators. It is not clear that they're going to scale up. But the fact that you can etch these Josephson junctions on a chip means that you have some promise of scalability.
Yeah.
Right.
So that was my question. As in, how are you? Even if you take all the costs of supercooling, etc., and because these are all possible today, and we are not really talking about mass computing, etc. Just all these demo that Google or whoever is doing. So what is it basically built on was my basic question. Leave out the cost. I mean, eventually we can always bring the cost down.
Right.
So the core of it is still some kind of a silicon germanium today, and it may be some other form of silicon.
Right.
Back to it's a sort of something similar. Right?
Yeah, it is similar. I would say it's basically any sort of 2D material with some superconducting properties on which you can etch these Josephson junctions. Right. So that's sort of what the base is. Well, there are other, like I said, architectures. So there are what are called nitrogen vacancy based qubits. That again is, I think there are other companies that are trying to do that as well. There's a big group in Delft, which is trying to build these nitrogen vacancy based qubits. Those qubits are basically nano diamonds where you have removed a carbon and replaced it with a nitrogen, and then there is a kind of vacancy because of your atomic numbers are different for carbon and nitrogen. So that's called a nitrogen vacancy center. It's a kind of nuclear spin based architecture. That architecture is considered nice because instead of liquid helium, it's sufficient to cool up to liquid nitrogen temperature. And these are considered more room temperature qubits. But every architecture comes with its own issues. So at this point, it's not completely clear what the future is going to be. But Yeah, the things that have been scaled up best are the superconducting Josephson junction based.
So one area of research is going to be creating these, the qubits and the material. There's going to be a lot of technology there, and the one which will give you more coherence and something that does not, where the noise can be reduced, so that you can have more and more circuits and your calculations can happen.
Exactly.
So far now, let us say that I assume that there is a black box.
Yeah.
There's a company like Intel or some company will come and create this and give it to me. Okay? I'm just trying to sort of make it as trivial as it is possible for me to understand.
Yeah.
So that is going to be one technology strand, and there's going to be a lot of work.
Yeah.
The second is having something there. How to make use of it? It could be algorithms. It could be basically building the communication to that and doing basically making use of it. Let's say that's the hardware part of it.
Yeah.
But then there is the software part of it. Right? Now that's where I was a little unclear when you mentioned that there is a P and literally all problems can be put into P, NP and NP complete. Let's put it in that kind of a box. Right? Today in the general computing world, we have been solving comfortably all the P category problems.
Correct.
Right? It's about any numerical simple computations, multiplication, division, square root, all the things that we are familiar with, any kind of string processing, and between them they pretty much cover your your image processing, your audio processing, your video processing. Right? End of the day, leaving out some of those fairly complex, for example, the factorization problem, the code breaking problem. Right? Now, if you keep that aside for a minute, and many other unsolved problems, what is the whole? What is the value that a quantum computer will give me?
Yeah, that's a very nice question, and it reminds me of. So I have written Scott Aronson's name here. So he blogs. He's a very avid blogger, and his blog articles are something that I would highly recommend. It's called Shtel Optimized. He writes a blog which kind of puts quantum computing in perspective. And the byline of the blog says, not all NP-hard problems are solved by quantum computers, right? So it is not that quantum computers are going to just solve every problem which is hard for a classical computer and so on. Nor is it clear that they're going to completely replace or eliminate our classical computing devices. But there are two things that I would like to focus on in this aspect, in this relation. So the first is the original idea why a physicist was interested in quantum computing. Of course, there are two categories of physicists who are interested in quantum computing. One was people like William Wouters and David Deutsch, who merely wanted to explore what it would mean to use quantum states as information carriers, right? And then they came up with Deutsch algorithm, no cloning, etc. Then there was Richard Feynman, right? Richard Feynman, who famously came up with this. I mean, there's this nice article or this kind of interview of Feynman on quantum computing, right? So he's considered by many as a father of quantum computing, or at least a terminology quantum computing. His idea was as follows, that we have several problems in physics which we cannot simulate efficiently on a classical computer. And this continues even today. I could think of several problems in condensed matter physics where I would like to identify interesting topological phases of materials. This cannot be done efficiently on classical computers. Quantum field theories, quantum chromodynamics cannot be solved efficiently on a classical computer. I need big super clusters.
Can you just expand that, as in why quantum chromodynamics problem cannot be solved?
It's the size of the system, right? It's the sheer size of the system.
It's talking about the number of computations that you need to do to solve a given equation numerically.
Yeah. But if I want to simulate these quantum systems, then what better than a quantum system itself, right? So this was Feynman's original interest in quantum computing, the idea that you could simulate quantum field theories, quantum many-body physics directly. That if this is a computation that nature is able to do somehow efficiently and arrive at the ground state of a system, then if I build a truly quantum device, then that device should be able to simulate for me efficiently.
Isn't it a little misleading? Because a quantum problem by itself, trying to say that, here you are trying to create a computational device which takes your quantum modeling equation that you have written and then numerically trying to solve that. Now, simulation indicates, on the other hand, that you are sort of, let's say that I'm trying to solve the hydrogen atom problem.
Yeah.
I'm just, oversimplifying.
Exactly.
Right?
Yeah.
Then you are sort of trying to create that exact thing, and then there is a proton or a quantum particle at the center, and then there is another particle coming around.
No. So it is not quite as simple as that, no, because my computing device is still only this sort of digital logic.
Yeah.
It's still
so what does
0, 1,
Feynman mean by
so today one of the biggest use cases is in quantum chemistry, where people would like to understand, for example, band structure, electronic structure, right? So there are what are called variational quantum eigensolvers, where it takes a bit of intuition and cleverness to design a quantum algorithm which is really going to solve this Hamiltonian for you, right? You still have to program your quantum computer to solve it. But the fact that your quantum computer can exist in superposition, can explore the Hilbert space. If I were to use, I avoided using that term throughout the talk, but it can explore the quantum phase space directly for me, right? As opposed to a classical computer, which does not truly explore a quantum phase space, then that gives me an advantage.
No, I understand where my problem comes. I am still thinking of solving the problem in classical manner, and I'm really looking at only the quantum computer as something that can speed up the calculation. Okay, you are saying that you can actually create algorithms which exploit the quantum
nature of
themselves,
your device.
The structure of quantum itself to do these things, perhaps way faster, and that's of course, I mean, it's way beyond me to even conceptualize it, but I understand where it comes from.
Right.
So in a sense, the early part of computing was all about solving possibly the Newtonian mechanics-ish kind of a problem. I mean, I'm again oversimplifying that. And when the scale of the problem increases, that's where even supercomputers struggle to the current classical supercomputers struggle to solve that in terms of the time required, etc. And here we are probably going to see very different approach itself in terms of building algorithms to solve the problem.
Exactly. So in fact, the supremacy thing, quote unquote supremacy, that Google showed is essentially a random sampling problem, right? What Google showed the speed up in using the 72 qubit machine is that it can produce the output of a random circuit exponentially faster than a classical circuit can do. Because of course, a classical circuit is deterministic and has to go through every sequence of events, whereas a quantum circuit has a natural way of exploring these events and giving you these sampling randomness more efficiently, right? There was even a recent news about a Chinese company which implemented what is called boson sampling efficiently. This again is a demonstration of a supremacy experiment, if you will. And again, it's making use of the inherent randomness in quantum mechanics to do this.
There is one question by somebody called Attangare Shanmugam. Has there been any progress made on BQP on NP complete problems?
It is still not clear, right? It is not that the advent of quantum computing or these classes has solved the NP versus P debate, right? It's still a big open problem whether NP is equal to P or not. And BQP does not address this. In fact, what we now have is what is called a sequence of polynomial classes. It's called a polynomial hierarchy. And at the top of it is NP complete. And of course, if we found a polynomial time quantum algorithm, which would solve an NP complete problem, we are done. Because that will then tell you that all NP problems are now solvable easily by a quantum computer, but that doesn't seem to be the case so far. And that's why the complexity thing I drew, avoiding the NP complete.
It was sort of somewhere in between. I mean, in
correct.
NP to P
it did
range.
Not intersect. It does not intersect NP complete, so we don't know of an NP complete problem which can be solved in polynomial time on a quantum computer.
Okay. Now, going back to the more fundamental aspect that you had given in the very beginning of all those circuits that you showed.
Yeah.
Now, when we were studying in school, it was fairly easy for us to, I mean, I don't know whether it is easy, but at least it was easy for us to understand the and or gates and how zeros and ones change, and the fundamental binary mathematics was sort of mapped onto how we are going to do computation, whether it is adding numbers, multiplying numbers. Now, from there, it is still a little bit difficult for me to visualize the very basic operation. Of course, I understand your matrix transformation, etc. Now, how do we introduce something like this at a school level of how, for a minute, ignoring the quantum computing. See, when we were studying binary mathematics, it was not, though there will be a statement like, this is what is used in computing, etc.
Right.
We could actually understand it as a standalone kind of a thing. Now you are in a sense talking about a set of coherent mathematics, which is at the base of quantum computing.
Yeah.
Now, how do we introduce that now at a school level? I'm not talking about all these white hat junior code, that kind of a thing. Right. It's just that, theoretically, we need to really understand how the qubit-ish way of calculating and computing things is done, so that people start relating to that and start thinking of mathematics at that level, which then maybe somebody maybe bright youngsters will come up as quantum algorithmists who can then do interesting stuff. So are there attempts at trying to make it accessible to school children by any chance?
Yeah, so I'm sure there are. For example, I know of, say, different institutes. Even NUS in Singapore runs workshops for high schoolers, let's say, on quantum computing. And I myself have tried to give similar lectures for high schoolers and so on. My own intuition and understanding is that if you can understand basic matrix algebra, right, and if you can showcase the qubit as just a vector, right? And one simple way of visualizing vectors is, of course, using your real three-dimensional vectors, right? One is at school level, we do get introduced to vectors, right? Now, we just have to introduce the same idea of vectors in a matrix language, right? And then you are used to doing some, maybe in school, not so much, but if you can talk about rotating vectors, like I showed the qubit as some kind of polarization vector, right? Or I showed this as in 3 dimension as a vector on the surface of a sphere. So, and then you think about how do you rotate a vector? What do you need to do to rotate a vector? You break it up into components, and then you try to, act on those components, etc. So I think starting from real 3-dimensional vectors, one can build this idea up of the idea of linear vector spaces, right? Without really going into the formalism of it too much. And perhaps then one gets some handle on how these things transform and so on.
I fully understand that, rotation vector is something that anyway it's already there in the syllabus. Maybe, in the 10th, 11th, 12th, they will be able to understand that. Then you are also, in a sense, introducing complex numbers. At least when you are visualizing a combination of that, maybe breaking it up, possibly will give them the basics. But I'm talking about using that for computing. For example, in the basic binary introduction, eventually you show that you can actually add 2 numbers, you can multiply 2 numbers by those, shift as an operator, which will result in multiplication by 2.
Correct.
And then you can always, then there is a converter. Given any number, you can convert it into binary, then do all the manipulation, then convert the outcome back into the base 10 number, right? Similarly, using the quantum algorithms, doing operations and getting results. I'm just saying, there is, I have not explored it. merely asked if there was anything. That was a primary thing.
Yeah, so you're talking about some basic quantum logic and quantum programming in some sense.
Right.
I frankly think that's a little bit hard. See, because it's a two-step process still, right? The problems are, let's say, arithmetic in nature. Let's say something like prime factorization, right? So the first thing, I want to factorize some big number into its prime factors. I have to write down its binary representation. Then I have to write down a quantum state that corresponds to that binary representation. And then I have to think about how I can manipulate that state and so on, right? So that first step is something that's easier to teach because it's just going from base 10 to base 2, right? And it's easy for me to write down the binary string associated with that number. And then there is the Boolean algebra that kicks in. But now you have to think about encoding it in a quantum state. And so that's a slightly, I mean, it's, I think it's hard to avoid the classical computation aspect. And so you have to kind of build on it. So I don't see a way around that.
Okay.
Right? Yeah.
Okay.
Yeah. But you're absolutely right that the complex part of it is certainly very important.
Right.
There are people who have tried to look at what are called re-bits, okay, real quantum bits. That if you don't have a complex factor, how much can you do? And you cannot do much actually. It is
but given that complex numbers are already there as part of the syllabus, why avoid that? It can be just brought.
Yeah, exactly.
So, there's a question from a person with the name Euclideology.
Okay.
Saying, can two pairs of things be in a superposition? I don't know exactly. Can you make sense of the question?
I am going to understand it as, can I have two quantum states in a superposition, or can I have more? I mean, that's kind of the entanglement that I showed, right? The way I introduced entanglement was to show that I can have two photons or two quantum bits, right? Together, two quantum bits form a four-dimensional system. Just like how 2 bits, if I have 4 possible strings. Two quantum states form a four-dimensional system. And of course, in this four-dimensional system, I can have superpositions, right? And certain special superposition states are what become entangled states, actually.
Yeah. Okay, great. Then there are generally questions about how is, a fairly simple question of how are these quantum computers more advantageous than classical computers? One is speed, but is there something that you can concretely say 0.1, 2, 3, 4, this is how a quantum computer, despite its costs and complexities, are more advantageous?
Yeah, one is the speed and the other is the inherent randomness, which can be made use of. For example, today, in fact, the question that you had asked me earlier about, what else can I do? I didn't mention this word again, which is a buzzword today, quantum machine learning, right? So if I were to think of building learning networks, right? Again, rather than just use classical learning networks, naturally, if I use quantum logic in that, if I build quantum Bayesian networks, which people are very much working on today, people are working on quantum neural networks, quantum machine learning algorithms, and so on. So the inherent randomness may have some advantages, like I explained with the two supremacy experiments that have happened, and so on. So I would say these are the two main.
Okay. I think part of the problem is that we have to understand certain quantum mechanical ideas,
yes,
which should be sort of internalized. Otherwise, the mind only thinks of speed. So it's much more than speed, is what you are saying. Basically.
Yes, it is much more than speed. There is an inherent probabilistic nature which can be quote unquote exploited or used for certain tasks today, right?
Okay.
So,
okay. Then there is one question again, also from Mr. Euclideology. Why did Michio Kaku say that silicon age must end for Moore's law is going to be false in about 10 years, which is more related to silicon?
I frankly am not an expert on the classical, I mean, in the sense the current trend where Moore's law is going, etc. I mean, I just showed that people are today talking about a kind of inverse Moore's law in the quantum case in terms of the number of qubits they're able to manipulate and control coherently over long periods of time. I don't think I can comment on the classical situation. I'm not qualified, I think, to comment on that.
Okay. Great. Now, just to round up a few questions, where is India right now in quantum computing, both at the university level and at any kind of private or government initiatives in trying to build quantum computers?
That's an excellent question. And again, something that I didn't have time to dwell on. Okay, so I think the government over the last maybe 2-3 years has taken serious steps to invest in quantum computing research, right? So today we have maybe at least a dozen research institutes across the country, which work both on theoretical and experimental aspects, right? So IIT Madras itself, for example, we have a theory group and we have an experimental photonics group. So there was another aspect of this whole thing which I didn't touch upon, which is the quantum cryptography aspect, right? So somebody asked about what else can you do?
Right.
And you can do quantum cryptography, which promises to be more secure in certain ways than your classical crypto systems. So there are several labs, both in IIT Madras, in Raman Research Institute, in Delhi, and so on, which work on cryptographic aspects. Then there are labs in TIFR, in IISc, Bangalore, which work on implementing quantum bits in IISER, Pune, different kinds of architectures. There's superconducting labs, there are NMR labs, there is an NV Center lab coming up in IIT Madras. So I would say that while we were not, say, the leaders in this, we certainly today are present on the quantum map, right? And the government has launched 2 schemes. So about 3 years ago, they launched a quantum science and technology program. DST launched a QUST program where they held several meetings. They called quantum researchers from across the country, have call for projects, etc. And more recently, there's been a national mission on quantum technologies, which has been announced with a reasonable amount of money put in. I think the idea is that the government at least seems to want to see experimental efforts in particular on quantum computing. Theoretically, I would say that we have been in the game for a fair while now, but experimentally today we are starting to be in the game, is what I would say. Private players, unfortunately, we don't have too many. In fact, there's barely one such private player that I know of, which is a company in Bangalore called QNew, which which works on implementing quantum cryptography, something called quantum key distribution. There are government labs which are today getting interested. I mean, over the last 3-4 years, I've seen government labs such as DRDO, CDAC, etc., which are getting much more interested and which are talking to researchers, say IISc, IIT Madras, etc. Collaborations are building up. But I would say it's a work in progress. And yeah, unfortunately, we are not leading the efforts yet, but I would say we are definitely in the
the reason why I asked the question is also a little political, right? If you look at our own computing, access and growth, at various points in time, even though the computers have been built by private entities based out of the US, the US had prohibited exporting dual-use technology products. So for quite some time, getting a Pentium processor computer to us in the 1990s required all kinds of complexities.
Right.
Supercomputer, you had to basically invest and build it yourself. Now it reached a stage where today, for example, by just putting together, because of large scale, you can put together network devices, multiple network devices, and drastically speed up computing. Today, anybody sitting anywhere can actually build a high amount, large computing capability. Let's put it that way, using the classical computing paradigm. Tomorrow, if Google or IBM will build supercomputers, quantum supercomputers, let's put it that way.
Right.
If the US says India will not get it, India will not get it.
Yeah.
So we will have to build it ourselves.
Exactly.
And that is something that we have to consider with a lot of urgency. We may be using it for some astronomy calculations or some, if you want to land a probe on Mars, you may need certain, high-speed computations for simulations, etc. And you cannot be waiting for some government to give us approvals to get that. Our research, is our research in data processing and high-end science and technology will be seriously affected if you don't have access to that. So and you clearly pointed out that private companies, we don't have many. We probably have one or at best two. The amount of money that is required, I don't think private funding can flow into it. So it is, by and large, it's going to be only government and university.
Yeah, but I do think that private players also have to pitch in at some point. I often find Indian tech companies, even in some conversations that one has had with them on this issue, to be somewhat skeptical in the sense of, you're absolutely right. I would say that quantum science and technologies today is a strategic asset of some form. Today, IBM is willing to put its 50-qubit computer on the cloud and give some limited access. So even when I teach a course in IIT Madras, I allow my students to go on the cloud, right? So this is, by the way, something I encourage the audience also to do. You can log into IBM's website using your Google account, your Gmail account, and you can implement the Deutsch algorithm, which I just showed you on IBM, right? So they give you a 6-qubit computer on the cloud. There is something called Amazon Bracket, where you can go and buy access to IBM, Rigetti, IonQ, a few different companies. So they are today willing to, like I said, a pay-per-use kind of model where you can go pay and get some access, right? And we encourage our students to do that simply because they get trained to think, like you said, how do you think about programming a quantum computer? How do you think about what to do when you have a quantum computer at your disposal? However, on the hardware side, to actually do the nuts and to do the chips or to do the implementation, that is where I think serious effort needs to go in. And I do think that we have woken up, maybe a little bit late, but in the last 3-4 years, I see some serious efforts both from government and from government labs to do this. But I also think private players should also invest, like Indian companies, Indian tech companies should also, invest in this. And I think that more concerted effort, definitely building more manpower is needed. It's very possible, like you said, a few years from now, Google and IBM say that we can no longer give you access to our quantum computers. And then
at least fortunately now we have quite a few IT services companies and SaaS companies which are multi-billion dollar in terms of valuations and profits. So hopefully if some of them at least start investing and at least compete with each other, maybe we will have quite a bit of quantum computing research and hardware building that may happen here. Wonderful. Thank you for the lecture. I know it's a little difficult topic. It's not the easy popular science kind of show few pictures. It involves some physics, some mathematics, and you did a wonderful job. Thank you. Thanks a lot for your
Thank you. I hope people had some takeaways from it. And like you said, I find it hard to introduce without a little bit of physics and mathematics. And I think it's also important to some extent to appreciate or try to understand some of the physics and math behind it. So I hope, I managed to convey the excitement.
Thank you once again to you and all our viewers. So we will meet again next month with another lecture on a science or technology topic from Varahamihira Science Forum. With that, we will end this lecture. Thank you.
Thank you. Bye. Thank you. Bye.